Hey there. So we're going to finish our notes on Module 2, Lesson 3, Forms of Energy, because we did not get a chance to do it in class. So I figured I would just go over it here right now and then let you fill in the answers as you're watching this. So we had already kind of answered the first third right here, talking about the number of carbon atoms, C for carbon. And I got that because right here in propane, it says C3, and that means there are 3 carbons. So if I take a look at the number of hydrogen atoms, it says H8, so there are 8 hydrogen atoms. And then for oxygen, I'm going to look over here at oxygen gas, because remember, I'm counting the number of atoms for the start of the reaction, so everything to the left of this arrow. And so that number, it says oxygen gas, which is O2, but then there are 5 of them. So I need to do 5 times 2, so I would get 10. Okay. Number 2, count the atoms of carbon, hydrogen, and oxygen at the end of the reaction. So to the right of the arrow, did the numbers change? So I'm going to do blue, bold. Oops. And bold. There we go. So on the right, for carbon, we still have 3. You can see, right, there's just 1 carbon right there, but there are 3 carbon dioxide, so there's still 3. Hydrogen, I've got 8. And then oxygen, there are 6 here and 4 here for a total of 10. So no, the number of carbon, hydrogen, and oxygen atoms stayed the same. So there we go. Number 3, explain how the left side of the reaction looks different from the right side of the reaction. So I would say that, bold and blue. On the left side, we have propane and oxygen gas. Then on the right side, we have carbon dioxide, water, and heat and light energy. So the elements from the left side were rearranged to form the compounds on the right side. So we underwent a chemical reaction to turn propane and oxygen gas into carbon dioxide, water, and then energy, heat energy and light energy. So can combustion reactions occur on Earth? Explain. Bold and blue. Yes, it happens all the time, right? It says right up here, this chemical reaction takes place in a camping stove, in some welding torches, and in cars, right? Combustion engines. So yes, this occurs on Earth all the time. Moving on to nuclear fission reactions. I'm going to scroll down a little bit. So atom bombs get their energy from fission of uranium-235 atoms. Neurons can split these atoms into 2 smaller atoms and release more neurons that can go and split more atoms. So when we talk about fission, right, we're pulling it apart. So what is needed to make a nuclear fission reaction happen? Well, I need uranium, what was that, 235, right? That's my starting point. So like up here, right, we had to start with propane and gas for combustion. For fission, we're starting with uranium-235. What happens to the uranium atom at the end of the reaction? Is it still uranium? Explain. No. The uranium is broken apart into with that krypton and barium atoms. I don't need this. So krypton, yes, like Superman, and barium. How do I spell that? Barium. So no, it is not still uranium anymore. It has been pulled apart through fission to create two smaller elements, barium and krypton. Can nuclear fission occur on Earth? And then explain why or why not. The answer is yes. We do nuclear fission all the time. We use nuclear fission in bombs and then in power plants, right, to run some of our cities, even countries, if we're talking about Japan. So yes, nuclear fission is occurring all the time. The biggest problem is how to store that depleted uranium. That's the question. The third type of reaction is a nuclear fusion, right? So fission pulling apart, fusion putting them together. So fusion is the joining of two light nuclei to produce a heavier one. Mass is lost and a tremendous amount of energy is released, even more than the energy released in nuclear fission. Solar energy is a form of fusion energy. When two isotopes of hydrogen combine at very high temperatures to form helium, fusion occurs. A diagram of nuclear fusion is shown to the right. So we've got two different isotopes of helium, I apologize, two different isotopes of hydrogen fusing together to make helium. They lost a neutron and we got energy from that. So what do both hydrogen atoms have in common? So we're looking at these two hydrogens right here, and the thing that they have in common, they both have one proton, singular proton, right? This red one, they both have one proton. So then number two, how are the two hydrogen ion atoms different? They have different numbers of neutrons, right? Because these are isotopes, and if you go on to take chemistry, we'll talk more about isotopes. But for now, I can just see that this isotope has two neutrons, and this isotope has one. How is helium different from hydrogen? Gold and blue. Helium has two neurons and two protons, where hydrogen has one proton and either one or two neurons. Sorry, I almost misspelled neurons there. Oh, look, I did. Neutrons. There we go. A helium atom has two protons and two neutrons. How does a uranium atom size compare to a helium atom? Here, bold and blue. Because it has two protons and two neutrons, uranium is a much larger atomic number than helium. Uranium has 92 protons to helium's 2 protons. And I know this from the periodic table of elements. Explain how the left side of the reaction looks different from the right side of the reactants. So the reactants versus the products. So I start with, bold and blue. Eek. Bold. So on the left side, we have two helium atoms. And on the right side, helium has undergone fusion where it lost a neutron and energy was released. So we've got 2 helium, I said helium, these are hydrogen. Yeah, so on the left side, we have 2 hydrogen atoms, and then they fused together, right? Fusion into helium. We lost a neutron, and from that reaction, a tremendous amount of energy is produced. And so the last question, can nuclear fusion occur on Earth? It can, yes. Get rid of that 3. But the amount of energy required to start this reaction is much too high. So it's much more than the amount of energy that would be produced. So it's just not a sustainable energy source right now. It takes way more energy put into the system to actually fuse the hydrogen ions than what we would get out of the reaction. So it would be, it'd be like spending $10 and then getting $8 back, right? I don't want to do that. I'd rather spend $8 and get a $10 item, right? So it just costs too much right now. So this last part, comparing the reactions. So read the reaction characteristics in the chart below and put an X under the type of reaction that each characteristic is describing. Okay, so talking about combustion, nuclear fission, nuclear fusion. So number 1, has occurred on Earth's surface. Bold and blue, and then I'm just going to put an X. Yes. That has combustion occurs on Earth all the time. So does fission, so does fusion. Involves the rearrangement of atoms. Yes, all 3 of them. We are rearranging the atoms in some way or another. Number 3, involves the splitting of large atoms, right? That is going to be fission, splitting apart. Involves the combining of small atoms, fusion. Process that produces the radiant energy in stars. That is nuclear fusion. Produces the radiation that travels to Earth in waves. Again, fusion, because it's coming from the sun. Can produce heat and light energy. That is going to be combustion, right? It said at the top, produces heat and light energy. Number 8, reaction responsible for the atomic bomb. That is nuclear fission, right? We started with uranium. Involves the element uranium. Okay, well, I already answered that one, nuclear fission. Occurs inside a car, combustion. Occurs inside a nuclear power plant. That is going to be nuclear fission. Involves the elements hydrogen and helium. That is fusion. Involves the elements carbon and oxygen. That is combustion. And then down here at the bottom is just an image of our electromagnetic spectrum, starting with the smallest or shortest waves, moving to the longest waves. We mostly focus in this kind of, not quite midway, but the visible light spectrum. That's what is what we're concerned with when it comes to solar energy for photosynthesis and sustaining life on Earth. So there we are. We have finished Module 2, Lesson 3 notes. If you have any questions about chemical and nuclear reactions, please be sure to let me know. Thank you.